Hey, good morning. We have today and then one more day on Monday talking about Chapter 3. You probably should have read Section 3.11 on heat capacity already because I mentioned it last class, but that's the last section to read. Homework 2 is due today, and homework 3 is due a week from today. That's the homework for Chapter 3. We'll talk a little bit about those problems. And then a week from Monday is Exam 1, and you should already have the practice exams about those. And we'll be talking about those next week. Maybe just a little bit about Exam 1 at the end of the day if we have time. So any questions on where we are and what we're doing? Okay. Then let us do one more example on Boltzmann factor. We were talking about the Boltzmann factor last class, and we did several examples. I wanted to show you one more example, this one from bioelectricity, which is a favorite subject of mine, and what we'll be talking about in depth in chapters 6, 7, and 8. So let's just consider a cell. Now let me tell you the way that a physicist, especially a physicist who does bioelectricity, thinks of a cell. Okay, here's a cell. It's got inside, which is salt water, and it's got an outside, which is salt water. And it's got a membrane, which is an insulator in between the two. There. All right, so that's my view of the cell. And there's going to be a voltage across the membrane. So there's a voltage in here, and you always measure voltages relative to some reference. We're going to take the reference at the outside. So think of the outside as being grounded. The inside is at a voltage V. What we want to do now is we want to develop a Boltzmann factor approach to understanding what that voltage is. So you have to really think of this as a two-state system. You can have a charged particle that can either be inside the cell or outside. And the energy from basically the electrical potential energy is going to be, so it's charge times the voltage. So the Q, which would probably be we're going to be considering mainly sodium, potassium ions when we're talking about bioelectricity. So it's going to be the charge on a single ion. So basically the charge on an electron, but positive sign. And times the voltage. And that's because voltage, if you remember back from your basic electricity, voltage is really a potential energy per unit charge. So if you take potential energy per unit charge and multiply it by the charge, you get the energy. So you have a two-state system now. On the outside, the voltage is 0, it's grounded, so the energy is 0. On the inside, you have an energy QV. So what we want to do is we want to figure out the probability of being outside, and that was, let's do the probability of being inside first. That was the Boltzmann factor. This is one of the equations you want to remember. It's got a constant times e to the minus, and the energy, which in this case is going to be Q times V over Boltzmann's constant times the absolute temperature. That's the Boltzmann factor that we discussed last class. On the inside, it's going to be the same thing, except now V is 0. I mean, on the outside, V is 0. So you get e to the 0, which is 1, and it just gives you the constant. So now we know P in and P out. If we wanted to, we could figure out C by saying the sum of these two has to equal 1, normalization. But what I really want to look at now is the ratio of P out over P in. The nice thing about the ratio is the C's cancel out, so we don't have to worry about the C. And we just get this ratio. Well, this would be in the denominator. So we get, when it comes up with the numerator, the minus becomes a plus. The C's cancel out. It just becomes e to the QV over KT. All right, now, here's where I'm going to wave my hands a little. I'm not going to prove this exactly. But the probability of being outside versus the probability of being inside is really related to the concentration outside to the concentration inside. And we're going to assume they're proportional. You can either think of this as being a bunch of degenerate energy states, or you could just take my word for it. Probability is going to be proportional to the concentration. It's a little bit of hand waving, but I'm going to say that this is going to be proportional to the concentration gradients. One more thing, concentration of what? Well, we're going to be talking about a cell at rest. We really want to calculate the resting potential. And a cell, when it's at rest, can have potassium ions cross the membrane, but sodium ions and other ions are completely blocked. So we're going to assume this is a membrane that can pass potassium ions only. So that means the outside, that's potassium concentration outside, over potassium concentration inside, is going to equal E to the QV over KT. So that's really analyzing the voltage with the Boltzmann factor. Now all I want to do is I want to solve this for V and find out how to calculate the V. T, by the way. Okay, so we'll take the log, natural log of both sides, and that will kill off the exponential and give us a log over here. And then we'll have to multiply through by KT over Q, and we'll get V is equal to KT over Q log potassium concentration out over potassium concentration in. So there's a relationship between the resting potential and the potassium concentrations. And this is actually known as the Nernst potential, and it's the Nernst equation. So the Nernst equation is really nothing more than the Boltzmann factor, but just solved for a different variable. Okay, so let us see. We need two things of interest. First of all, there's KT over Q. Well, let's calculate what that is. That's going to be the K is the Boltzmann constant, which we said was 1.4 times 10 to the minus 23 joules per Kelvin, times temperature, which we're going to take to be our standard body temperature, 310 Kelvin, divided by Q. Q is the charge on the potassium ion. Potassium is singly charged, so it's the charge of a proton. It's minus the charge of electron. 1.6 times 10 to the minus 19. And that's coulombs. And a coulomb unit of charge is just a joule per volt. That's because if you divide by V, you get a charge is energy over voltage. So if you calculate that out, well, there's something wrong here. What is this? This is minus 3. How in the world? That is the Boltzmann's constant, which is a much smaller value, 27. I'm sorry about that. Boltzmann's constant is 1.4 times 10 to the minus 20, and is it even 7? No. I really should wear my glasses all the time. 23. Okay. Sorry. Now, if you do that calculation, this is a small number, but so is that. So it's actually only like a factor of 10 to the 4 smaller, which is going to cancel out. This comes out to be something that's a little bit less than 0.27 volts, which is 27 millivolts. So KT over Q for a singly charged ion is 27 millivolts. And that tells us the order of magnitude of the voltage across the membrane. The only thing left to ask is what are the concentrations. So we're going to look at a typical cell. A typical cell has, well, a little bit of potassium outside. The outside of cells tend to look like seawater. And seawater is mostly, the salts is mostly sodium chloride. There's only a little bit of potassium. So I have about 5 millimolar. But on the inside, you have more like 150 millimolar. A lot of potassium on the inside. So when you take this ratio, you're going to get the log of, the outside is 5 over 150, which means the log of 1 over 30. Now the log of a number less than 1 is going to give you negative. So this log, if you calculate it on your calculator, comes out to be minus 3.4. So the voltage, which we'll call the resting voltage of this cell, is going to be minus 3.4 times kT over Q, 27 millivolts, comes out to be minus 92 millivolts. And that's a little large for a resting potential, but it's sort of just about what cells have for their resting potential. So we can calculate the resting potential of a cell just from the Boltzmann factor. Now you might be wondering, how in the world does the cell maintain this concentration gradient? And that we'll talk about in chapter 6. But basically, the cells expend a huge amount of metabolic energy just pumping potassium ions into their cells and sodium ions out. So we'll go about that in chapter 6. But I wanted you to see one more example of the Boltzmann factor. So that is our discussion of the Boltzmann factor. Were there any questions about Boltzmann factor, either that example or anything from previous examples that we did on Wednesday? Okay. Boltzmann factor is sort of a microscopic relationship. It tells you how the population of individual energy levels. Now we're going to talk about something that's more of a macroscopic thermodynamic idea called heat capacity. Now I'm going to erase this, and then we'll talk about heat capacity. So, heat capacity. Let's take this definition as a change in energy over a change in temperature. So if you add a certain amount of energy to an object, how much you get increase its temperature, that depends on its heat capacity. And if this is, if you know energy as a function of temperature, this kind of just becomes the E dt. T being temperature. And that means that if you want to find out how much energy you have to have in order to raise its temperature a certain amount, it's C times delta T. So heat capacity has units of energy over temperature, typically joules per Kelvin. Now, we're going to just do an example of an ideal gas and try to calculate the energy of the heat capacity of an ideal gas. And now I'm going to do one more hand waving. The energy of an individual molecule, so I'll use small e for the energy of an individual molecule, on average is 3/2 kT. Okay, a way to interpret Boltzmann constant times temperature is basically it's on the order of the energy individual molecules have. And then the 3/2 comes from, if you do a careful analysis, which we aren't going to bother getting the 3/2, but it's on the order of 1. So, if we want to know how much energy there is in a large volume of gas, well, we'll just add them up. We'll say the energy of a mole of gas molecules. So you have a mole of air, basically. And a mole of air at normal pressure and temperature is sort of a box like this big. Okay, and how much energy is that? Well, that's going to be the energy of an individual particle times how many particles there are in a mole, which is Avogadro's number. So you get Avogadro's number times 3/2 kT. Now, Avogadro's number times K. Does anybody know what Avogadro's number times the Boltzmann's constant is? Anybody either read or remember from maybe a chemistry class? The gas constant. If you remember the gas constant from the ideal gas law, that's equivalent to Avogadro's number times the Boltzmann constant. So this becomes then 3/2 RT if you want to use the gas constant. Now the question is, what's the heat capacity of that mole of gas? Well, the heat capacity is just going to be the E dt. So here's the energy, and we take the derivative. It depends linearly on the temperature. We take the derivative, all we get is the 3/2 R. So 3/2 R is the heat capacity. It's the molar heat capacity. So the heat capacity of 1 mole. And you can calculate that, and that comes out to be, well, let's see. First we need the R, the gas constant, which you can either just take from chemistry or you can multiply Avogadro's number, 6 times 10 to the 23, and that would be molecules per mole, times Boltzmann's constant, 1.4 times 10 to the minus 23, and then be joules per Kelvin. And you do that calculation. This calculation works out very nice because this is 10 to the minus 23 and this is 10 to the 23, so they just cancel. And you see 6 times 1.4, which comes out to be 8.3. If you didn't round things off, it would be 8.3 joules per Kelvin mole. That's the gas constant. And therefore, we predict from this idea is that the specific heat is going to be 3/2 or 1.5 times that, or about 12.5 joules per Kelvin mole. That's per mole. And that should be the specific heat of an ideal gas. Now, that should be pretty close to the specific heat for air. Air acts like a pretty good ideal gas. In fact, though, if you measure the specific heat for ideal gas, you will get, well, I've gotten a little ahead of myself. I want to get specific heats per unit mass first. So we have the specific, molar specific heat. Now, what I'd like to do next is I'd like to get the molar heat capacity. Now I want to get the specific heat capacity. Specific heat. Okay, who can tell me how the specific metabolic rate was related to the metabolic rate? Anybody remember that? By the mass. So the specific metabolic rate was the metabolic rate per unit mass. Same thing here. The specific heat capacity is going to be the heat capacity divided by the mass. So you can find per unit mass. And that means we can get the heat capacity of a mole of gas, which we calculated, divided by the mass of a mole of gas. Okay, so the specific heat, the heat capacity of a mole is 12.5 joules per Kelvin mole. And the mass of a mole, well, let's assume it's all nitrogen because air is mostly nitrogen. And so we want the mass, well, we can find the mass of a given molecule, which is, it's all N2. N2, so it's diatomic. So 2, and nitrogen has a molecular weight of 14. So 14 times the mass of a proton, 1.67 times 10 to the minus 27 times Avogadro's number, if you want the mole of the mass of a mole. 6 times 10 to the 23. And you calculate that out, and you get 446 joules per kilogram Kelvin. So the units of heat capacity are generally joules per Kelvin, or if you want to do 1 mole, joules per Kelvin per mole. But the units of specific heat, which is usually given the symbol C star, is joules per Kelvin per kilogram. Okay, so that's our prediction. Yes?
Why would you multiply by the mass of the proton in Avogadro's?
Because you want the mass of a mole of this gas. So you know that there's Avogadro's number of atoms, or of molecules, and you need to know the mass of 1 molecule. So the mass of 1 molecule is, it's diatomic N2. There's 14 protons and neutrons in each nitrogen atom, and each one has this mass. Another way of doing it would be to say, well, you actually have, you know that the molecular weight just means you have 14 grams per mole, and then convert it to kilograms, and you get the same result. It's just 2 ways to approach it. I usually think of this atomic weight as just being a pure number that tells you how many protons and neutrons you have.
Okay.
That's the way I'll do it. All right. Yes.
So you can just do 2 times 14 grams per mole and convert that? Like you don't
You
necessarily need to do that way?
You can do 2 times 14 grams per mole times 1,000. Let's see, 1,000 grams would be a kilogram. And that would give you, for the denominator, 2 times 14 divided by 1,000. That would give you 0.028. Whereas if I just do the denominator here, because this involves the numerator and denominator, let's just get 2 times 14 times 1.67 minus 27 times 60 to the 23, and I hope I get the same thing, and I do, 0.028. So either way you do it will give you the mass in kilograms, which is the grams of a mole. That'd be kilogram per mole, which is what you want if you're looking for the mass per mole. Either way works, whichever you're most comfortable with. But you can't use 14 grams per mole and then forget to convert to kilograms. Otherwise you'll get in trouble. All right. Now, if you actually look up the specific heat of air from experimental data, it's a little bit different. Its order of magnitude's right, but it's actually more like 1,000 joules per kilogram Kelvin, and that's measured. So you might wonder what in the world is going on. Why is our prediction about a factor of 2 off? And it turns out the problem is that if you want to use this idea of an ideal gas is a bunch of point particles. But really, nitrogen, diatomic nitrogen, is not a bunch of point particles because it can actually have vibrational modes. Here's your nitrogen and N2, and they're connected by like a spring, and the spring can have modes where it oscillates. If you did everything correctly, you'd find that you'd get the experimental measured version. But if you treat it as purely an ideal gas with no internal modes of vibrations, you get a somewhat smaller number. So here we have our specific heat of air. Okay, you can also do the specific heat of water, and we like to compare air and water. However, we don't have an easy way to calculate that, so I'm just going to give you the value. Water, it turns out, water is a very effective way to store heat. In other words, it has a very high specific heat capacity. 4,218. So over 4 times air. So water's large specific heat is going to be important in biology because we're mostly made out of water. Now, sometimes it may seem like the specific heat's even more different than this. And that is if you talk about specific heat in terms of per unit volume instead of per unit mass. So let's just talk about heat capacity per unit volume. What you can do is you can say that the C star per unit volume is going to equal, well, I won't call it C star. I'll call it C star per unit volume. That's going to equal C star per unit mass times the mass, which would be rho times volume, but we're doing it per unit volume. So you just get the heat capacity per unit volume is C star what we calculated times the density. I just want to show you what happens if you do that. If you take C air times the density, specific heat of air times the density, well, we know the density of air is 1.2, so you get 1,200 joules per kilogram, not per kilogram anymore, we're getting it per meters cubed. But if you do the same thing for water times the density is 1,000. So you get a big factor for the density, and you get a big factor for the heat, and you end up getting 4,218,000 joules per meters cubed Kelvin. So if you think of heat capacity as per unit volume, water has vastly, vastly more heat capacity than air. If you think of them per unit mass, water still wins, but not by nearly as much. All right, so let's see how we can use this idea of heat capacity before I erase this. Were there any questions about heat capacity and the values so far? All right, then let us look at, we'll just talk a little more here. Here's all this. We're going to want to look at how things heat up, and the reason why we have warm bodies and why we're warm is we have a certain metabolism. We talked about the metabolism earlier. We talked about scaling. For a human, the metabolism is about 100 joules per second, or in other words, 100 watts. Kind of like an old-fashioned light bulb. That's a typical human's heat capacity, or metabolic rate. So we can actually learn something. We can try to calculate how much energy we use in one day. So let's see. This is energy use per day. Well, this is a rate. This is 100 joules per second. So if we want to get the total energy in one day, we got to figure out how many seconds there are in a day. And you can do that. There's 60 seconds in a minute. There's 60 minutes in an hour, and there are 24 hours in a day. So 24 times 60 times 60, that comes out to be 86400 seconds per day. And you do the calculation, and you get 8.64 times 10 to the 6 joules per day. So about 8 million joules, almost 9 million joules each day is what we have to what we need to maintain as our metabolism produces. Now, chemists don't like to use joules. Chemists always want to use moles. They want to use they don't like joules. They want to use calories. So 1 calorie is equal to 4.186 joules. So if I do the conversion, 1 calorie is 4, so I divide this by about 4. It comes out to be 2.06 times 10 to the 6 calories per day. But now, if you're used to counting calories, you might say, that doesn't sound right. We need 2 million calories per day. But that's because the nutritional calorie that people use when they're talking about nutrition is usually given a capital C, and it's 1,000 times the little calorie. Sometimes it's called a kilocalorie. But usually the big C calorie is what you see on the cereal boxes and all the other food lists. So that's a factor of 1,000. So that means you got 2.06 times 10 to the 3 of the big calories, which means 2060 calories per day. And that's about right, isn't it? About 2,000 calories is what we need to eat. So that's what we need in order to produce our metabolism. And you can also talk about specific metabolic rates, which is R over unit mass. So a typical human's about 70 kilograms. 100 over 70 is going to be about 1.4 watts per kilogram is our specific metabolic rate. All right, so let's put these two ideas together. We want to take, what we want to do is now we want to suppose you turned off all your ways of cooling. So you're usually in steady state, usually your temperature is constant. What we're going to do is we're going to wrap you up in some thermal blanket so we totally eliminate your ability to get rid of heat. How fast are you going to heat up? Because your metabolism is going to keep going, keep producing heat, but you have no way now to get rid of the heat. So let us see if we can figure out how fast you heat up. Well, that means how fast does your internal energy increase? And that's just equal to your metabolism. But how fast your energy increases is the same as saying how fast does energy change with temperature times how fast does the temperature increase. Because if you think of this as this calculus statement as just being algebra, the dt's cancel, and this is d little t, temperature. So big T temperature, little t is time. All right, and this, what's this? What did we say that was? That's heat capacity. That's the definition of heat capacity. So C, d little t. So, the change in energy with time is C times the change in temperature with time. Equals R. So in other words, the rate of increase of temperature is going to depend on your metabolic rate, and it's also going to depend on your heat capacity. And you might say, well, that depends on how big of a person he is. The metabolic rate depends on what your mass is, and so does C. But if you do everything per unit mass, you do it in the numerator and the denominator, if the mass cancels out, that's the same as R star and your C star. So it should be pretty much the same for all animals and all different sizes of people. Assuming, this all assumes you have no way to get rid of the heat. So let's see what this comes out to be. R star, we said, is 1.4 watts per kilogram. And C star, which was on the previous page, for water, because we're going to treat our body as just being water, is going to be 4,218. That would be joules per kilogram Kelvin. Watts really a joules per second Kelvin. So watts of joules per second, excuse me. So the per kilograms cancel, the joules cancel, you get Kelvin per second. So if you do the math, you get 0.00033 Kelvin per second. Now here's some good news. If you're dealing with just time derivatives, it doesn't really matter whether you measure temperature in Kelvin or Celsius, because they have the same size degree. There's just a constant between them, and if you take a derivative, the constant goes away. So this is the same as 0.00033 degrees Celsius over per second, which is a little more easier to think about, because at least, I don't know about you, I'm more used to thinking of Celsius than I am thinking of Kelvin. And that looks like a really small number, and that's good news. You wrap yourself up in a thermal blanket, and you don't immediately spike a fever and die in a few seconds. But if you can't get rid of the heat, you do slowly warm up. And how much after an hour? How much would you warm up after an hour? So what's your delta T after 1 hour? Well, that's just your rate times an hour. And an hour is 60 times 60, or 3,600 seconds. So I take this and multiply by 3,600, and I find that you get 1.2 degrees Celsius every hour. So now it's something a little bit more severe, because if you go up several degrees Celsius, that's going to be a very high fever, and you get in few hours, half a day, you're dead. So this gives you an idea of the heat capacity and what its implications are. It tells you how long you can survive if you couldn't get rid of the heat. Okay, now you have a problem 3.48 that's in your homework assignment. It's the last problem. And the problem 3.48 is really talking about a very similar calculation. So your body must dissipate energy from metabolism at 100 watts. Suppose mechanism stopped working. In fact, it's almost identical. I almost did, maybe exactly did, problem 3.48 for you. So those of you who are here, or those of you who are watching the video, that homework problem should be fairly easy. Okay. Questions? All right. Then let's do another homework problem. Let's do another problem having this heat capacity, which is going to be 3.49. This one's not in your homework, but that doesn't mean you should listen. This is a classic type of homework problem for thermodynamics. Okay. 3.49. A person of mass 70 kilograms, body temperature 37 degrees, breathes half a liter of air at temperature 20 degrees. So this is just you outside. It's not a cold day, but sort of a room temperature day, breathing in air. Assume there are no other sources of heat. So we're going to forget about metabolism for a second. And the whole body as a whole is insulated, so there's no heat's lost to the environment. I want to find the equilibrium temperature between the air and the body. So in other words, this is equivalent to the problem of you have an insulated bucket full of ice water, or full of water, at cold water, and you drop a hot steel ball in it. Not so hot that it boils, but a hot steel ball. You know, the whole thing comes to equilibrium, and what's the equilibrium temperature? So we're doing the same thing, but we're doing it by breathing in air and then letting the air and the body come to equilibrium. And this can be important because on a really cold winter day, you're breathing in real cold air. Is that having a significant cooling effect on your body or not? So let us see if we can calculate that. What the equilibrium temperature will be. This is problem 3.49. You have your body, which is going to be 37 degrees Celsius. And it has a heat capacity for your body. And it's going to be in equilibrium with this air, which is 20 degrees C, and it has a heat capacity for air. And the whole thing's thermally insulated. And initially, there's a barrier here, and then we remove the barrier and let things come to equilibrium. And we want to know the final temperature, T, once the temperatures are the same on both sides. Okay. So, first thing we need to know is the body, which is the higher temperature, is going to lose a certain amount of heat. And use a certain amount of that heat is going to go into heating up the air. So heat lost by the body is what? How do I calculate the heat lost by the body once it comes to equilibrium? What's the relationship between heat and change in temperature? Change in heat, or heat lost, versus change in temperature. Somebody help me out here.
The heat capacity.
Heat capacity. So this would be heat capacity of the body times, this is the change in energy, so you got the change in temperature. What's the change in temperature between the initially and the final? It's going to initially be 37, and it's going to finally be T. T is going to be less, because it's going to go down, and your body's going to decrease in temperature. So this is a positive number, and it's the heat that's lost by the body. We can use Celsius because we're taking a difference, and therefore it would be the same whether it's Celsius or Kelvin. And heat gained by the air that you put into your lungs. It's just C air times, and now it's going to end up with T, and it's going to start at 20. T is going to be between 37 and 20, so you really want T minus 20 here. You want positive, since I'm calling this gain as opposed to loss, this one you want positive 2, because heat's coming into the air. So there's those two, and when it reaches equilibrium, those two have to be the same. The amount of heat really is conservation of energy. The amount of heat that you lose by the body has to be gained by the air. So you get that C body 37 minus T equals C air and T minus 20. And we want to solve for T. So it's just a matter of solving this for T. So let's put all the T's on the right and all the stuff that doesn't have T on the left. So here is C body times 37. And here is sea air times 20. It's got a minus sign, but I'm going to move it over to this side, so it's plus sea air times 20 equals. Well, this factor has a t, a plus. This factor has a minus, but I move it over to this side. It has a t with a plus. So I'll factor the t out, and what's left, sea air plus sea body. So the final temperature is going to be sea body 37 plus sea air 20 divided by sea body plus sea air. So you can see what you're getting is just sort of a fractional change. You can multiply this one by sea body over sea body plus sea air, and this one by sea air over sea body plus sea air. So it's going to be, that's just going to be the fraction of heat capacity due to the body, and that's going to be the fraction due to the air. Okay, so we calculated the final temperature. Now all we need to do is we need to actually calculate what these numbers are. So I want to know what the heat capacity of this person is. Well, we figured out what the specific heat was for water, basically, and we're going to treat the person just as water, which is a pretty good approximation, times the mass of the person. So that's the mass of the body. Okay, so we found that the heat capacity for water is 4,200 joules per Kelvin kilogram. And the mass we said was 70 kilograms. So that comes out to be, not right, this should be the specific heat. And the specific heat turned out to be 4,218. You can use it as 1,8. Times 70. Let me just do that calculation because it doesn't look right like this. 4,218 times 70. And that comes out to be, I guess it really does get that big, 295,260 joules per Kelvin heat capacity. Let's do the air. That's C star for air times the mass of the air. How am I going to get the mass of the air? I can take the density of the air times the volume of the air. This is a little more complicated. We can do this. We know the specific heat capacity is 1,000 joules per Kelvin kilogram. Okay, the density of the air, back from about 2 or 3 classes ago, is 1.2 kilogram per meters cubed. And the volume of the air, it says in the problem, is half a liter. That's about what you get when you have a breath. You know, maybe not a really deep breath, but a standard breath. Okay, but we got a problem. Here we have meters cubed and here we have liters. So how many, 1 meters cubed is how many liters? What's the conversion? 1,000. That's 1,000 liters. So you do that calculation, and this number, 1,000 here is going to calculate the 1,000 there. So you basically get half times 1.2. You get 0.6 joules per Kelvin. So what we conclude is, gosh, the specific heat, or the heat capacity of air, that air we breathe, was really, really tiny compared to the heat capacity of our bodies. And that means our temperature, if we do the calculation, and I'll leave it to be the numbers in, comes out to be 36.99997 degrees C. So the bottom line is, when you breathe in cold air, it does cool off your body, but only a tiny, tiny bit. And you'd have to use a whole lot of breaths in order to begin to see an effect. And that is ignoring any way to maintain your temperature. So breathing in cold air, it has some issues with, you know, how your lungs feel and things, but as far as cooling your body off is not a really big thing, even though that air does heat up. And the other thing to remember is that your air doesn't cool off your body much. It's basically your body warms up the air is what's happening. All right, so another example of heat capacity and its impact on humans. All right, questions on that? Alrighty. Got one problem left I want to do with you guys, and that's problem 350. And that's also not on your homework, but it's one of my favorite problems in the book. One thing we don't talk a whole lot about in our book is evolution, but actually a lot of the physics we're studying strains and sets limits on what evolution can do. And this problem 3.50 really talks about the evolution of dolphins and whales. So let's see what it says. Fish are cold-blooded and they breathe water. That is, the water goes past the gills and they extract the oxygen from the water. Could a fish be warm-blooded and still breathe water? Well, this gets down, it doesn't actually talk about dolphins, but it has implications for dolphins, because a dolphin is a mammal. So a dolphin does live in the water and does breathe. It is warm-blooded, but the dolphin cannot develop gills and act like a fish and stay warm-blooded, because the dolphin has to go up and breathe air. And we're going to see why. Basically, it gets down to why sharks, cold-blooded, can breathe water. Dolphins, warm-blooded, have to go up and breathe air. So let's see if we can figure this out. So here's the notes. Okay, so a dolphin is going to, or let's consider the fish. Let's suppose the dolphin is going to develop gills and try to live that way. Well, how do gills work? The gills basically mean that a bunch of seawater flows past the gills and it extracts oxygen from the seawater. So that's a process, a lot of seawater to extract a little bit of oxygen. So basically you have to consider the blood volume of the fish or the dolphin and compare that to the amount of water that it processes. And it processes a huge amount of water in order to extract a little bit of oxygen. So the heat capacity of all this water it's processing is huge compared to the heat capacity of the blood, just because it's a volume difference. There's a lot of volume has to go by, and that means that if you were breathing through gills, you're basically taking the blood and you would have to cool it down to the temperature of the surrounding water. Because in order to transfer the oxygen and process all that water has a huge heat capacity, and we just found that means the final temperature, is going to be essentially the temperature of the surrounding water because of the heat capacity. So, if a warm-blooded animal and you tried to breathe through gills, basically the blood that goes through the gills is going to be cooled off to the temperature of the surrounding water. Then you got to warm it back up, or else it won't stay warm-blooded. So let's see how much energy it takes to warm back up. And let's use as our standard, you want to get 1 liter of blood. And how much energy does it take to warm that up? So the energy to warm. Okay, that's going to be C times change in temperature. And C is basically going to be the specific heat of water times the mass, which is density of water, times the volume, which is going to be 1 liter, times delta T. So we're going to see this combination C star rho V a lot. C star for water, I'm just going to round it off, 4200 joules per Kelvin kilogram, times the density of water, 1,000 kilograms per meters cubed, times the volume. We're going to consider 1 liter of blood. So 1 liter of blood, I'll just do the conversion, that's 1,000th of a meters cubed. 1,000th meters cubed And the change in temperature, okay, we have to assume some difference in temperature between the warm-blooded animal and the surrounding water. We're going to take 20 degrees. 20 Kelvin, 20 degrees C, either way, it works. And that would be going from 37 down to 17. So it's not a freezing cold water, but it is pretty chilly water. Do that calculation. What you get is 84,000 joules. It takes 84,000 joules to warm up 1 liter of blood back up to the body temperature. Now, why do we breathe? Why do we take in oxygen? We take in oxygen so we can run our metabolism and we can produce heat. How much heat do we produce from the oxygen you get in 1 liter of blood? And we're not going to calculate that. I'm just going to tell you what it is. The energy you get if you take 1 liter of the oxygen that's in 1 liter of blood and you use it all to make metabolism, you get 4,000 joules. So now you see the problem. The dolphin can't win if it tries to use gills because the energy it takes to warm that blood back up to its body temperature is much greater than the energy it gets to run its metabolism. So it doesn't pay to even breathe. If it doesn't pay to breathe, it'll suffocate. So you can't have a warm-blooded animal breathing through gills like that. Just the heat capacity considerations won't allow it to work. So how does the shark work? The shark's the same temperature as the surrounding water. So everything, same argument except delta T is 0. It doesn't take any energy to warm up the shark. So it gets some energy from bringing in the oxygen and it can use it to run its metabolism. It just works just fine. So you can be warm-blooded and live in the sea if you go up and you breathe at the surface like a dolphin or a whale. And you can be cold-blooded and live in the sea like any fish, including big sharks. And you can use gills, but you can't do both. Be warm-blooded and use gills because of physics. So no matter what evolution tricks can try to do, there's no way it can defeat these kind of ideas about heat capacity. So that's just a little bit on how what we're studying constrains biology and in particular constrains evolution. Alrighty. So, I think that's all I have for today. Hopefully you can, if you didn't hand in your homework yet for Chapter 2, bring it up. Try to get started on Chapter 3 over the weekend so you can bring in your questions. We can ask questions on Monday or Wednesday. But I will see you all on Monday.